that on the intake stroke, fluid enters the pump through a check valve. On the forward stroke, the check valve closes, sealing off the inlet. Therefore, the fluid displaced as the piston is moved forward must flow through the pump outlet. The pressure is determined by the workload. This principle applies to all positive displacement pumps, whether they be vane, piston, or gear type. Perhaps the simplest and easiest to understand is a gear pump. One gear driven by the drive shaft meshes and rotates another, called the driven gear. Both are contained within a close-fitting housing. A partial vacuum is created at the inlet as the gear teeth unmesh, and fluid flows in to fill the void. Then the fluid is carried around the gears to the pump outlet. As the teeth go back into mesh, oil is forced out through the outlet port. As this operates, we now have high pressure at the outlet and less than atmospheric pressure at the inlet. This condition is referred to as unbalanced hydraulic loading. Gear pumps today are highly efficient units, capable of operating at pressures of up to 3,000 psi and speeds in excess of 2,000 RPM. This performance is at least partially the result of the addition of bronze-faced flexible wear plates. These plates are pressure-loaded against the side faces of the gears, reducing clearance to a minimum. Passages in the wear plates also permit oil, under pressure, to extend farther around each gear to reduce the unbalanced hydraulic loading inherent in this type of pump. Sperry Vickers gear pumps range in size from 7 to 50 gallons per minute at 1,200 RPM, although considerably higher drive speeds are permissible. They're available as both single and double units. Other manufacturers have gear pumps that are rated as high as 100 gallons per minute. Vane pumps seem to have been favored in the machine tool industry, perhaps because of their high efficiency, low noise level, and long life. In an unbalanced vane pump, a slotted rotor is splined to the drive shaft and revolves inside a cam ring. Vanes are fitted into the rotor slots and follow the inner surface of the ring as the rotor turns. A minimum starting speed of 600 RPM will throw the vanes out. Then, centrifugal force and pump outlet pressure under the vanes hold them against the ring. Pumping chambers are formed between the vanes and are enclosed by the rotor, the ring, and two side plates. With the ring offset from the center line of the rotor, the chambers increase in size and take in fluid as they pass the pump inlet port. Then, as they cross over center, the chambers become progressively smaller and fluid is expelled at the pump outlet. This pump has a somewhat limited pressure capability because of its unbalanced hydraulic loading. Its displacement, however, can be varied or even be reduced to zero by moving the ring towards the center line of the rotor. Now, a balanced vane pump operates in the same manner as an unbalanced unit, the difference being that the inner contour of the ring is an ellipse rather than a circle. This configuration forms two sets of pumping chambers. They're on opposite sides of the rotor, but are interconnected through passages within the housing. Forces caused by pressure buildup on one side are canceled out by equal but opposite forces on the other. The displacement of a balanced design vane pump cannot be adjusted. However, interchangeable rings with different cam contours or widths are available, making it possible to quickly modify a pump to increase or decrease its delivery. Another modification we sometimes require is to reverse the drive shaft direction. We would, however, have to ensure that the flow direction within the pump is not reversed. The key to this situation is in the repositioning of the ring so that the major diameter of the inner cam is rotated 90 degrees from its original position. By doing this, the pumping chambers will continue to increase in size as they pass the inlet porting and decrease at the outlet. Flow through the pump will then remain the same, even though drive shaft rotation has been reversed. Now, let's focus on three different types of balanced vane pumps Sperry Vickers currently manufactures. All are similar in operation, but differ in construction and pressure capabilities. We'll first discuss the pump patterned after the original model, patented by the company's founder, Mr. Harry Vickers, in 1925. Called the V104 series round pump, it has a replaceable pumping cartridge, which consists of a ring, rotor, and vanes sandwiched between two bronze bushings, each containing 2 inlet and 2 outlet ports. Hubs on the rotor fit into supporting hubs in the bushings, which serve as bearings. The drive shaft only requires a small pilot bearing in the pump cover and a somewhat larger one at the front to accommodate any minimal side loading. A 2-diameter pin keys the cartridge assembly together and fits into one of 2 holes in the pump body, which are located 90 degrees apart. The hole that we select determines whether the pump is assembled for right or left-hand rotation. The pump cover serves as a clamp to hold the cartridge assembly together. Care must be exercised when tightening the cover bolts, as over-tightening may cause the pump to seize. Under-tightening will result in loss of efficiency. The V104 is an extremely quiet and efficient pump, but its pressure and drive speed limitations of 1,000 psi and 1,200 RPM limit its use in many of today's applications. So, where higher pressure and drive speeds are required, as in most mobile vehicle applications, the Sperry Vickers Model V20, or square pump, is more apt to be found. With permissible speeds up to 3,400 RPM and pressure capabilities of 2,500 psi, it's well suited to many vehicle applications.